Hey, welcome back. Continuing our discussion of chapter 1 and some length scales and other interesting facts about the universe. It turns out the universe we in astronomy have an advantage over some other fields in that we can observe the past. In most cases, if you want to know what the past was like an archaeologist would have to go and dig up, I don't know, ruins and examine pottery shards to find out bits of scrap food that might have been preserved to figure out what diets might have been like and make total guesses about what the past was like for people. In astronomy, we actually have it pretty easily. All we have to do is look far away and we are looking back in time because light travels at a finite speed. Now that speed is really fast. It's 300,000 kilometers per second, which is enough to get to the moon in a second, which is enough to loop all the way around the Earth 8 times in a single second. So on our everyday, ordinary life scale, it's extremely fast. But on the scale of the universe, on the scale of the solar system even, it's not that fast. Things are so far apart that it takes light some time to get from one point to the other. So as I said, it takes a full second for the moon, for light to get from the Earth to the moon. It takes a full 8 minutes for light to go from the sun to the Earth. A full 8 minutes. What does that mean? Well, it means that we're not actually seeing the sun as it is now. When you look up and see the sun, which you should not do, you should not look up and look at the sun, but the sunlight that's reaching you, you go out on a sunny day, that sunlight, that light that's hitting you left the sun 8 minutes before. If you were to look at the sun, you would be seeing it as it was 8 minutes ago, because that's what we're seeing right now. And again, this is a very small part of the universe. Sirius, which is the brightest star in the sky, it's not the closest star in the sky, but it's the brightest star in the sky, it takes light 8 years to get to us. The closest star in the sun in the sky is Alpha Centauri, and it would take 4 years for light to reach us from Alpha Centauri. So we're not seeing Alpha Centauri as it is now, we're seeing Alpha Centauri as it was 4 years ago. We're not seeing Sirius as it is now, we're seeing it as it was 8 years ago. Sirius could be gone, it could have blown up. It probably hasn't. Sirius doesn't change that much over the course of 8 years. But if it had, we wouldn't know. If it did today, we wouldn't know it for another 8 years, because the sun, the light that left it 8 years ago is just now getting to us. Andromeda Galaxy, that we saw a picture of in the previous video, is the closest large galaxy to us. And it's 2.5 million, it takes light 2.5 million years to get to us from that galaxy. In fact, the Andromeda Galaxy is the most distant object that you can see with your unaided eye. If you know where to look and you're at a dark site, you can look in the constellation Andromeda and see a fuzzy patch. Those particles of light that are entering your eye left the Andromeda Galaxy 2.5 million years ago and have been traveling through space, only to finally get absorbed in your retina and be visible to you. It's pretty amazing to think about. And so, again, we're not seeing Andromeda Galaxy as it appears today. We're seeing it as it looked 2.5 million years ago. And again, 2.5 million years is a long time on our time scale and on the Earth's time scale, but it's not all that long in galactic time scales, right? The Andromeda Galaxy is 10 billion years old or so. So 2.5 million years, it probably doesn't look any different now than it did much different now than it did 2.5 million years ago. But the point is, we're seeing it still as it was 2.5 million years ago. So the further back in look we distance, obviously, the further back in time we look. Here are another few examples, going through some of my favorite objects in the universe. Here is a prominent constellation that is visible in the sky these days. You've got, this is Orion, of course. If you go out in the early evening in January or February, and it's clear out, you should be able to see this high in the sky. It is famous, of course, for the 3 belt stars, but it's also famous for the other bright stars in the constellation. Just above the 3 belt stars is the Betelgeuse, which is a very red star. Rigel is a very blue star at the bottom. And even the stars Bellatrix and Saiph are pretty bright stars. But what's interesting is this whole region is a giant star forming complex. And the biggest of those star forming regions is right here. And in fact, Orion's sword, looks like a star to the unaided eye, but if you look at it even through binoculars or a small telescope, it looks like you can see it's actually a nebula. And this is called the Orion Nebula, and it's a giant star forming region. You can see a nice big telescopic picture of it here. Stars being formed down in the center. And so you get some very massive stars down here. Anyway, it's we see it as it was 1,500 years ago. It took like 1,500 years to get to us from that particular nebula. Okay, so this photo here is, if you want to know where to look, Pegasus is actually very large square, and Andromeda kind of comes off the bottom of the legs of the horse of Pegasus, which is kind of upside down in this picture. Cassiopeia is right here, and here is M31, the Andromeda Galaxy. And it kind of will look like that. If you get to a dark site and you know where to look, it will kind of look like a fuzzy patch. It won't look nearly like this. You need a big telescope and lots of exposure time to get this. But this, again, we're not seeing the Andromeda Galaxy as it was today. We're seeing it as it was 2.5 million years ago. When we'll be able to see what it looks like now? Well, in 2.5 million years, when that light gets to us, we'll be able to see what it looks like today. But of course, 2.5 million years will have passed, and we'll be 2.5 million years in the future then. So it's also true that somebody standing in Andromeda looking back at the Milky Way sees us as we were 2.5 million years ago. So if somebody had an ultra powerful telescope in Andromeda Galaxy and could see all the way to the Earth, they would not know that humans had evolved. They would not know that there were anything that even looked like humans roaming around on the Earth, because they'd be seeing us as we were 2.5 million years ago. Okay, that's fun. So it goes on further than that, right? The Andromeda Galaxy on this scale, where we've got the whole thing out here, is right in our backyard. There are galaxies that are tens of millions of light years away, hundreds of millions of light years away, billions of light years away. And I'm coining a phrase now that I haven't used yet, but it's important. A light year is a unit of distance, which is how the distance that light travels in 1 year. So this galaxy that's 7 billion light years away, we see it as it was 7 billion years ago. 7 billion years ago, that's half the age of the universe, right? Galaxies could have evolved quite a bit in 7 billion years. They have evolved quite a bit in 7 billion years. So we have an advantage in astronomy. If we want to know what galaxies looked like 7 billion years ago, all we need to do is go out and look for a galaxy that's 7 billion light years away. And it will show us exactly what a galaxy looked like 7 billion years ago, because we're seeing it as it was 7 billion years ago. In fact, we have discovered galaxies that are 12 and a half billion light years away. And we're seeing those galaxies not as they are now, but as they were 12 billion years ago, when the universe was only about 2 billion years old. And galaxies looked very different than they do now. And so we don't have to make educated guesses about how galaxies have evolved and how they've changed over time. All we have to do is look out, and the further back in space we look, further away in space we look, the further back in time we look. Okay, now I just coined this term. Let's be more specific. A light year is kind of a confusing unit because it's got year in its name. You might think it's a unit of time. It's actually a unit of distance. Is in fact the unit of the distance that a light can travel in 1 year. Now, as you know, that's really far, right? It takes a second to go from the Earth to the moon. It takes 8 minutes to go from the sun to the Earth. So how far is a light year? We can now use some basic formulas in physics to be able to determine how far a light year is. By the way, this you might get intimidated. Physics, it's a formula. Eek. Relax, it's actually not that bad. In fact, you intuitively understand this formula. You intuitively, if I had asked, let's say you're going 60 miles an hour, and I ask you how far you go in 2 hours, you are instinctively, without even thinking about it, going to apply this formula, do some algebra in your head, and figure that out, right? So this is even if you're intimidated by writing it down, it's an equation that you're familiar with and you use in your everyday life. So velocity is a distance, how far you move, and how fast you do it in, how long it takes you to get there. If you have those two things, you can calculate a velocity. If you have any of these two things, the cool thing about this physics stuff, if you have any of these two of these three quantities, you can solve for the third quantity. And so that's what we're going to be doing. Let's figure out how far a light year is. We know that velocity equals distance divided by time. I'm going to abbreviate that. V equals d over t. And let's move to the next slide. And let's actually calculate how far a light year is. And this will put into practice some of the things we're going to need this semester. So I know that velocity equals distance divided by time. The question is, which of these two do I know, and which of these do I want to know? I'll let you think about that for just a second. If I was in a, if we were Newton 202, I would ask this to, I would pose this question to the class and wait for somebody to answer it. But now you have to answer it. Everybody has to answer it. Which of these do we know, and which of these do we not know? Well, the answer is, we know what the velocity is because we know how fast light is moving, and we know what the time is because we know how long it's moved at that rate, right? Velocity is the speed of light, and time is a year. It's the distance. We now know the distance that light traveling at the speed of light could move in a full year. So we need to do some algebra first and solve this equation for distance. So let's brush up your algebra skills. I can multiply both sides by d. Nope, that's not what I wanted to do. I'm gonna brush up on my algebra skills. I'm gonna solve for d. I'm gonna multiply both sides by t. Multiply by t on both sides. That gets rid of the t on this side of the equation. They cancel out. And I can rewrite this, t times v equals d, and I can switch it around even to say d equals velocity times time. I can do time times velocity or velocity times time. It doesn't matter which order I put them in. Okay, now let's remember what v is. We know that v is the speed of light. And we determined before that that was 300,000 kilometers per second. And we know that t is 1 year. I'll abbreviate year with YR. Okay, great. Now, what do we do next? Well, we just need to plug these numbers in and we should be set, right? So we've got 300,000 kilometers per second times 1 year. Great. So you multiply 300,000 times 1 and you're all set. Except that this is where we have to think about units. And units are going to be important. And so this is good advice for anything you do in this class, ever, really. You want to, anytime you write down a number, think about what those units are, because the units will matter. And sometimes you'll need to change the units in order to make good things happen. So here's an example where we want a distance. Kilometers is a good unit of distance. But here we have a unit of year on top and we have a unit of second on the bottom. We ideally like those two to cancel out, but they do not. Years and seconds do not cancel out. We need to, in fact, do a unit conversion to be able to put this in a form that things will cancel out and we'll be left with an actual unit. Okay, so let me explain quickly how I do unit conversions. You ready? I do unit conversions by, in order to do unit conversion, you have to know, for instance, how many seconds there are in a year. If I knew that, I could do this in one step. I don't know how many seconds there are in a year, but I do know how many days there are in a year. And so I can do let's convert years to days, and that will be the first step in the process. So in order to convert years to days, I need to know an equivalency. I need to know that 1 year is equal to 365 days. This equivalency, this equality, means that I can take a ratio of 1 year to 365 days or 365 days to 1 year. And since those two things are equal, that ratio will be equal to 1. And I can multiply any number by 1 and not change its value. And that's what I'm interested in doing down here. I'm interested in changing this 1, not changing the value, the quantity a year, but change the unit. And since I can use this ratio, I can change the units. So I need a ratio to multiply this by a ratio that has years. So years on top here, I need to cancel my years out. I want my years to go away. I want this years to go away. So I need my years in this ratio to be on the bottom, which means I need days on top. And so I can take this ratio, 365 days to 1 year, and look what happens. The years cancel out. Now, I've got days on top and seconds on the bottom. Well, that still doesn't work because days doesn't cancel seconds, but guess what? I know how many hours there are in a day. All I need to do is multiply by another ratio that has days on the bottom. I'll just put D, and hours on the top. And since I know that there are 24 hours in 1 day, my days will cancel out. I'm not quite done. I need to know that I need another ratio that has hours on the bottom, and let's say minutes on top. Since I know there are 60 minutes in an hour, my hours will cancel out. And finally, I know that there are 60 seconds in 1 minute. My minutes cancel out. And now finally, I have a unit of seconds up here that will cancel with my unit of seconds down here. So I can come back, I can cancel out seconds and seconds, and the only unit I have left now is this kilometer over here. So all I have to do, again, these are a bunch, 1, 2, 3, 4 different ratios, all of which were equal to 1, that took me from years to days to hours to minutes to seconds. And finally, those seconds cancel those seconds, and I'll be left with kilometers now as my units. So the numbers, I have to multiply these numbers together. 300,000 times 1, which is easy, times 365, times 24, times 60, gives me a number which is, you can check me on this, plug it into your calculator and see, it should be 9.46 times 10 to the 12. That's a 9. You move this decimal over 12 to the right, and that will give you the actual number. And what are the units? They are the units of, the only thing that is left that didn't get canceled out, and that is this kilometers. So a light year is 9.46 times 10 to the 12 kilometers. That's a big number. It's a really big number. It's even bigger than the 10 to the 11 numbers we were looking at earlier, but not quite as big as the 10 to the 22. So in the homework for next week, assignment 2, your job will be to calculate a light day or a light second or a light hour. It's the same principle, except instead of multiplying by 1 year, you'll be multiplying by an hour or a day or something like that. But you're still going to have to convert this to seconds in the end, so that the seconds will cancel out with your seconds, and you'll be left with a unit that's got more, makes more, is an actual distance unit. Okay, here's a question for you. How far is a light week? So I'm not even going to do this. Maybe I'll post the answer. Well, go ahead. So I will actually do it here. So you can have another example of how to do this stuff. But here's what I want you to do. I want you to do this on your own. Pause the video, actually practice this, and see how far you can get. And then come back and we'll solve it together. Okay, welcome back. Let's start again with our v equals d over t. Again, we want to solve for d. Multiply both sides by t. The t's cancel out. And we have d equals v times t. I know my velocity is still the same as it was before, 300,000, or you could say 3 times 10 to the 5 kilometers per second. And this time, instead of multiplying by a year, I'm going to multiply by a week. I can multiply now by 7 days in 1 week. And my weeks cancel out. I can multiply now by the same things I did before, 24 hours in 1 day, and 60 minutes in an hour, and 60 seconds in 1 minute. Yep. And all days will cancel out, hours will cancel out, minutes will cancel out, seconds will cancel out. And I will be left with 300,000 times 7 times 24 times 60 times 60, which is 1.8 times 10 to the 11. And the units, again, are, the only thing that's left here, kilometers. Great. Here's another interesting, fun question. We, again, if you think about the scale model of the universe where the sun is a grapefruit and the earth is a ballpoint 15 meters away, like we introduced in the previous video, how fast does light travel on this in this model? So again, imagine you are a superhuman giant in the solar system at this 10 billion to 1 scale. How fast would light appear to be moving on this scale? Pause the video, see if you can think about it, see if you can figure out, see if you can come up with a number, and we'll solve it together when you come back. Okay, welcome back. Let's do it. There's lots of ways to think about this. Again, you could take your speed of light, 300,000 kilometers per second, and divide it by 10, divided by 10 billion. That works. But in meters per minute, that takes some unit conversions, and it's going to take you a little bit to do that. So instead, let's think about this. We know that we've already learned some things that it's going to make this actually pretty easy. We also know that the distance, let's say, again, velocity equals distance divided by time. In this case, we want to know the velocity. Do we have a distance and a time? Let's think about this. Well, we know how long it takes, how long it takes in this scale. We know how far away the Earth is from the sun in the scale, right? It's 15 meters. And we also know how long it takes for light to get from the sun to the Earth in this model. It's 8 minutes. Right? So all we need to do is divide 15 by 8. You get something like 1.875 meters per minute. Is this fast? 1.875 meters per minute. This is actually really slow. In fact, I encourage you to set this up in your house or wherever you're living. Set up roughly a meter or 2 meters or whatever. So mark off 2 meters, roughly 6 feet, 6.5 feet or so. You know, if you have to get a tall person you know and mark their feet and their head somewhere in your room. And I want you to think about traveling from from the head to the tip, from that 6.5 feet, that 2 meter distance, in this many times 2 minutes, right? A single meter, it takes almost 2 minutes to make that trip. We're talking about multiplying that by 2, you get something like 3.7 minutes, almost 4 minutes to go 2 meters, 6.5 feet. On this 10 billion to 1 scale, where you are a really large being observing this happen, light actually doesn't travel that fast through the inner part of the solar system. So that's an interesting analogy to keep track of as you're thinking about, again, light moving really fast, but having to traverse the tremendous distances that are present even in the inner part of the solar system. Okay, we're almost done with our first class. I want to end with thinking about the scientific method. There's a lot of good stuff on this chapter as you're reading through. I encourage you to read through the full chapter and get all of this stuff. And I'm going to posted 2 videos in the page where this is linked. Richard Feynman, a Nobel Prize winning physicist, on how science works, which I think is entertaining and enlightening and informative, and then Carl Sagan on what science is and how it differs from say religion. But this is the basics. I'm gonna preach this semester a lot. These are the basics. Science works because it is testing. It's always tested against the universe. You make an observation. You think about that observation. You develop some model of the universe that's based on that observation. You use that theory to make a prediction. You then go out and observe and see whether that prediction comes true. Feynman says it better, but it's basically, if that experiment fails, if your prediction is wrong, then your theory is wrong. It doesn't matter how good it is or how good you are or anything else about you. The universe tells us whether your theory is right or wrong. And if your observations don't match the prediction that was made by your theory, you either have to go back to the drawing board and throw your theory out, or modify your theory so that it will meet the predictions. So that's how science works. That's how we've been making progress on understanding how the universe works for over 2,000 years. So please go ahead and, they're not long videos. Watch the video of Feynman on science, watch the video of Sagan on science, and we'll come back next week and start to think about some of the building blocks on which our understanding of the universe are built. So enjoy your weekend, and we'll meet back here next week.